Ever wonder how scientists peer deep into the Earth's crust to uncover hidden structures like oil reserves or ancient geological formations? It's like solving a giant puzzle with sound waves, except the puzzle pieces are seismic echoes, and the picture they reveal is the planet's hidden architecture. Today, we're diving into a revolutionary technique called Full-Waveform Inversion, FWI, that's transforming how we map the Earth's secrets. Imagine you're trying to map a cave system, but you can't see the walls. You drop a pebble into a hole and listen for the echo. The time it takes to return tells you how far the wall is. Now scale that up to the Earth's crust, where seismic waves from controlled explosions or earthquakes act like those pebbles. By analyzing their echoes, scientists use FWI to create detailed 3D maps of what's underground. It's like using a sonic MRI to see through the planet's layers, except the MRI is a supercomputer crunching data from thousands of sensors. But here's the catch. Traditional methods like the L2 norm struggle when data is noisy or incomplete. Think of it like trying to solve a jigsaw puzzle with missing pieces and a blurry photo. The algorithm gets stuck in local minima, like a maze with dead ends, where it thinks it's found the solution, but it's actually just a trick of the light. This is called cycle skipping, and it's a huge roadblock in seismic imaging. Enter the HV metric, a game changer in seismic inversion. This isn't just another math formula, it's a hybrid tool that blends the best of two worlds. On one side, optimal transport theory, which compares data by imagining how much mass you'd need to move to make one dataset match another. It's like rearranging furniture in a room to match a blueprint. But here's the catch. Optimal transport was designed for non-negative data like particles or money, things that can't go below zero. Seismic data, though, is signed. It oscillates like a heartbeat with positive and negative values. That's where the HV metric shines. It's a clever workaround that handles these signed signals while still capturing the movement aspect of optimal transport. The name, HV, stands for horizontal and vertical, two directions of deformation it tracks. Imagine a GPS that doesn't just tell you the shortest path, but also adjusts for elevation. By mathematically separating the data into these two components, the HV metric avoids the pitfalls of traditional methods. Let's break it down. Picture two jigsaw puzzles. The L2 norm is like counting how many pieces don't fit, simple but too rigid. The H2 norm is more like considering how all the pieces interact across the whole puzzle, giving a smoother, more nuanced comparison. And the H norm? It's a Goldilocks zone, balanced between detail and simplicity. The HV metric isn't tied to one approach. It's a flexible framework that can adapt its measurement style depending on the data. Here's where the math gets really interesting. When researchers tweak tiny settings called hyperparameters, like epsilon, lambda, and kappa, the HV metric shifts between these styles. Tiny values make it act like H2, perfect for spotting subtle, large-scale structures. Crank those knobs up, and it leans toward L2, which is great for straightforward comparisons. And with just the right settings, it balances everything in between, like a Swiss Army knife for seismic data. The proof. Researchers tested it on real-world models. Think of them as geological case studies. In the Marmousi and BP salt models, the HV metric outperformed traditional methods. While L2 created fake artifacts, and Wasserstein struggled with data quirks, the HV metric captured fine details without the noise. It's like having a telescope that adapts to any sky condition, revealing hidden stars no one else can see. This isn't just about fancy math. Better seismic inversion means safer drilling, more accurate earthquake hazard maps, and deeper insights into Earth's history. Plus, the HV metric skips the messy preprocessing steps required by other methods, preserving critical details in the data. It's a leap forward in turning noise into clarity. So the next time you hear about seismic surveys or oil exploration, remember, behind the scenes, tools like the HV metric are turning noise into clarity. The future of Earth imaging is sounding pretty clear, literally. Stay curious, and we'll keep breaking down the science behind the stories you hear every day. Until next time.